Now we're going to talk about text processing. The most basic and fundamental tool we have for text processing is the regular expression. A regular expression is a formal language for specifying text strings. So let's suppose that we're looking for woodchucks in a text document. Woodchucks can be expressed in a number of ways. We could have a singular woodchuck, we could have the plural s at the end, we could have a capital letter at the beginning or a lowercase, and any combination of these. So we're going to need tools to deal with this problem. So the simplest fundamental tool in a regular expression is the disjunction. The square brackets in a regular expression pattern mean any letter inside these square brackets. So lowercase w, capital W, square bracket means either a lowercase w or a capital W. So we can combine that with woodchuck to match lowercase or uppercase woodchuck. And similarly with digits 1, 2, 3, 4, and so on, 5, 6, 7, 8, 9, 0 matches any digit. Now that was kind of annoying to write. So what we'd like to do instead is have little ranges. The range 0 through -9, so square bracket 0-9 means any character inside that range. And the range A-Z means any character between a capital letter between A and Z. So let's see if we can see how that works. So here's an example of regexpal, a little tool we're going to use for regular expression searching. And we have a little text here from Dr. Seuss. We looked, then we saw him step in on the mat. We looked and we saw him, the cat in the hat. And let's try our disjunctions. So we can have the capital W and a lowercase w, and a capital W and a lowercase w, and that's going to match, as you can see, the capital W's and the lowercase w's just fine. Or we could have all the E's and all the M's, and that's going to match all the E's and the M's. Or in our ranges, we could have all the capital letters. There's all the capital letters being matched. We could have all the lowercase letters. There's a lot of lowercase letters there. Or we could match all of the alphanumeric characters. Think for a second how to match all of the alphanumeric characters. We can have... Or we could simply match some of the non-alphanumeric characters. We could have space and exclamation point in our square brackets, and that's going to match, as you can see, some of the non-alphabetic characters. Okay, so let's go on. Another kind of thing we might want to do in our regular expressions is negation in our disjunctions. We might want to say we don't want some kind of set of letters. So for example, we might want to say not a capital letter, and we can do that by saying caret A through Z in our square brackets. Caret, when it occurs right after the square brackets, means not. Caret A through Z, not a capital letter. Caret A, little a, means neither a capital A nor a little a. And caret E, caret, means not an E and not a caret. So you can see that the caret, when it occurs right after the square bracket, means not, but later on means simply just a caret. So let's take a look at that. So we can try finding all of the non-capital letters. Here's all the non-capital letters. How about all the non-exclamation points? Most things. And the non-alphanumerics. Sorry, the non-alphabetics. And there's just the spaces and exclamation points, as you can see. How about looking for a caret? Are there any carets in here? There are none. So there are no carets in, so nothing matches. Another kind of disjunction, which can be used for longer strings, is the pipe symbol, sometimes called or pipe, or just disjunction. So groundhog or woodchuck will mean either the string groundhog or the string woodchuck. So we can use the pipe symbol sometimes for the same thing as the square brackets. So A pipe B pipe C is the same as square bracket ABC. And we can combine these things. We can combine the square brackets and the pipe, so we can have groundhog or woodchuck, but use our square brackets for expressing capitalization at the beginning. And we can see that in our little example. We can have looked or step, and sure enough there, the words looked and step are both highlighted. Or we can have a disjunction of just random things. They don't have to be words. We can have all of the ats all of the ats and all of the ooks, and any random string is fine. Finally, there's sets of special characters that are very important in regular expressions. The question mark means that the previous character is optional, so the question mark after this U here will match the word color with or without the U, without the U, with the U. Then there are the two Kleene operators named for Stephen Kleene. Kleene star matches 0 or more of the previous character. So here's the star. It matches 0 or more O's. So we have one O followed by 0 or more other O's. So there's the initial O and 0 other O's, and then our H, exclamation point. Here's our initial O followed by one O, and then the H, and so on. 2, 3, and so on. Sometimes more simple, we can have the Kleene plus, so that means one or more of the previous character. So there's our O followed by the plus, meaning one or more O. So there's one O, there's two O's, three O's, and so on. And the dot is a special character meaning any character. So BEG dot N can match begin, begun, BEG 3N, it matches anything. And finally, two special characters. The caret matches the beginning of the line. So caret, capital A through Z, matches a capital letter at the beginning of the line. The dollar sign matches the end of a line. So A through Z dollar matches the end of a line, a capital letter at the end of the line. And then if we want to talk about a period, since periods are a special character, we have to escape them. Backslash period means a period. So a period by itself means any character. Backslash period means a real period. Let's go look at some of these. So here's the letter O. Here's 0 or let's make it one or more O first. Here's one or more O. So there's one O over here and two O's over here. And now let's look at beginnings and ends of lines. Here is capital letters at the beginning of a line. Here's capital letters at the end of a line. Oh, there aren't any. Here's punctuation at the end of a line. There's all the exclamation points at the end of a line. Here's all the periods. Remember, we have to backslash our periods, and if we didn't backslash the period, we would get all the characters, because period matches everything. All right, let's do one more example. Let's look at this little sentence here, the other one there, the Blythe one. Let's walk through how to search for words. Let's find the word, all the word the in this little passage. So think for yourself how you would do this. Well, the simplest thing you might do is just type the, T-H-E. And that does a good job of finding this the here. It finds this the and that the, but it misses these two thes. It also finds some other things. Let's fix the first problem. How do we not only get the thes in the middle, but those capitalized thes at the beginning? Well, we're going to use our disjunction. And sure enough, that correctly now matches the two beginning of line thes. But you notice that our pattern, although it now captures something it missed before, it still captures things it shouldn't be capturing. Other, there, and Blythe. So we need to augment our pattern. So how are we going to augment our pattern? We really want the when there's not an alphabetic character around it. We mean a space or a punctuation or something non-alphabetic. So let's just say non-alphabetic. Afterwards, great. That gets rid of other and there. Doesn't solve Blythe because Blythe has an alphabetic character before it. So let's go fix Blythe by saying non-alphabetic before it either. There we go. Now we found all of our thes. So we looked for the. We noticed it missed capitalized examples, so we added some. We made our pattern more expansive. We increased the yield of our pattern, but that incorrectly returns more things. So then we make the pattern more precise by specifying more things. This process that we went through is based on fixing two kinds of errors. One is matching strings we shouldn't have matched. We matched there, we matched other. And so that's solving the problem of false positives, or they're called type 1 errors. We were matching things we shouldn't match. And the other thing we went through is to solve the problem of not matching things we should have matched. So we missed those capital thes. And that's dealing with the problem of false negatives, or type 2 errors. And it turns out in natural language processing, we're constantly dealing with these two classes of errors. So reducing the error rate in any application, and we're going to see this again and again in this course, involves two antagonistic efforts. We're increasing the accuracy or precision, which helps us minimize those false positives, or we're increasing our coverage, or technically called recall, minimizing our false negatives. So in summary, regular expressions play a surprisingly large role in text processing. And the sophisticated sequences of regular expressions that we've seen very simple versions of are often the first model for almost any text processing task. For harder tasks, we're often going to be using, and we'll introduce these machine learning classifiers that are much more powerful, but it turns out even then, regular expressions are used as features in the classifiers and are very useful at capturing generalizations. So you're going to be returning again and again to regular expressions.